Good afternoon. Happy Friday. I am reaching out because I'm starting exam two, for exam two, which is nice. Why is it nice? It means that you get to actually test some statistics. We have done enough background, so we get to do not quite hypothesis testing, but we actually just get to do correlations and regressions. And correlations and regressions are really useful. They're one of the most important things that we have because sometimes we have to do observational studies. Sometimes we can't do an experiment. Sometimes just because of the way things work, we are pushed into because of the parameters of the study we're trying to run, we just can't manipulate stuff. So we have correlations. And correlations and regressions are great because they allow us to run a study even if we can't manipulate variables. The only drawback is we cannot prove causation. We can't say that the predictor variable or our X created the outcome variable or our Y, but we can say that they are correlated to a significant amount. Um, I'm going to explain a little bit about correlations, and I'm going to kind of show how to do one by hand in Excel, and then we'll get into the book. So this will probably be a long one, but I've gotten really good emails so far that people in the course like the way these videos are going. So I'm going to stick with it. If you have questions or want a different way, guess what? Just let me know and I'll change it up. So I'm sharing my screen, and I'm going to explain a little bit about correlations and what it actually is, what the formula is to get it, what R is, R squared is, and I'll show you all the steps and stuff. So here we go. I'm in 2 point intro to stats. I already did stuff for all these. We're finally up to 2.4, scatterplots, correlations, and regressions. This will be a long one, but hopefully it'll be useful. So I'm going to start by just showing you what the scatter plot looks like. So here we go. And let's say we want to think, does our, I don't know, exercise time affect our weight? Some real simple, right? So the more we exercise, we should lose some weight, right? That's kind of the deal. So this is our predictor variable in this case. And this is our outcome variable. For these regressions, the predictor variable always happens on the X, the outcome happens on the Y. And it's probably going to look something like this. Each one of these dots of my scatter plot represent a person. Then we have somebody who like super bulked up. Ooh, we can call this person an outlier up here. But this is what's called a negative correlation. Now, what does the regression do? This is the scatter plot. A scatter plot is just a set of the dots, and we have a negative relationship. Now, if I were to draw a line through this, this is the regression line. It's kind of like our line of best fit. The regression line basically just is giving you the best line or a trend between every one of these little points. That's all regression does. Gives us one of these for these points. Now we have R squared. These are the correlational coefficients. We'll talk more about them later, but I just wanted you to just like get a sense of what this is. The R shows you the direction, like positive or negative. It's always from -1 R to +1. So if it's a perfect -1, it just goes right down. And this is going to show us your strength, how strong it is. Every book, it's a little bit different, but and this is from 0 R squared. I'm pretty sure it's a capital R for the R squared. Obviously, the book might show something different, but if we're from 0 to 0.3, it's weak or no correlation. If we're from a 0.3 to a 0.5, we're at moderate. We're at a 0.5 to a 0.7, we're a strong correlation. And if I'm for anything from oh God, sorry, if I'm from a 0.7, sorry, that's really ugly. So if I'm from a 0.7 to a 1, it's very strong. I'm pretty sure that's the setup that they have for this. So this is a negative correlation or a negative relationship. We can't say that the exercise time caused the weight loss. We could just say this is significantly correlated that this will happen. Now, if you want to know exactly how to write these or how they're written, if you go back to the intro and we go to this guy right here, this thing that I made, this crazy long project, and you go to a simple linear regression, it'll show you exactly how to write the result statement for it, which is really nice, right? So in case you want to know exactly how it's done, it was found that the predictor variable, in our case, the exercise, significantly predicted the weight of folk. Then we got a B value and a P value. And I'll go more into this. Oh, that's cool. I'll go more into this, but that's like how it says. So isn't that cool? We're gonna do these by hand though. We got R squared, we got an F value, P value. I'll show you what all these are. And then they kind of show you how it looks like when it gets spit out of a Excel sheet. I guess I'll do Excel. I'll show you as much as I can show you. And we'll also do it on StatCard. So I'm going to show you like a ton of stuff. Hopefully it's not too much. Hopefully you're not overwhelmed, but I'll show you what I can show you. And then we'll look at the book. All right, sorry, let's go back into it. Here we go. All right, so that's my negative one, and I'll show you a couple more. Obviously, there should be a positive one too. So let's say study time and test scores. So probably the more you study, the higher test scores you should get. So they're probably going to look like this, which is pretty strongly positive. The closer they are to the line, the more strength it has, right? Probably never going to get a perfect one, but this one's very strong. The steepness is like kind of how strong it is. So if it's like less steep, if it looks like that, it's like moderate, and then like you can go to here, which is no correlation. So let's do one that'll probably have no correlation. Let me make something up. Why don't we do age and memory? Because like it should go like up over here, right? Memory scores, but then as you get older, it drops back down, right? So it should like kind of have like a little bit of a slopiness here. So like obviously your memory sucks when you're a baby and it gets really bad when you're older. But either way, if I were to draw a line through this, it'd probably be flat. Oh, probably flat, which is no correlation. So this one's going to be a positive correlation, positively correlated. This one's a negatively correlated. And remember, you can't say that one caused the other. Oh, sorry. This one is no correlation. We can't say that one caused the other. We can just say that they are related. Okay, so I think probably the next best thing is I can show you where they get this value from, this crazy value. So let's look up the correlation coefficient formula. Okay, doesn't that look scary, right? Isn't that a scary thing? This is like why in stats we let the computer do it for us, but we're gonna do it by hand. I don't know which one's scarier, but this is R, and then we just square it to get R squared. So what does this mean? This crazy thing. So here we go. I'll put this on the side, and I'll kind of tell you what each of these little parts mean, and then we will do one by hand. So here's R. This is an R squared, but this is R. N sigma xy minus sigma of x, sigma of y, and all of this is over the square root bracket n sigma of x squared minus the sigma of x squared. Notice this is different, okay? I got a little ugly. Minus the sigma of x. And then that is squared. Cool. And I'm assuming this is going to be times the same thing with y, right? Yeah. Sigma of y squared minus sigma of y squared. Cool. So now we don't need the formula anymore. I get a little confused. Sometimes I can't memorize all these crazy ones. So be sure it's, oh wait, is it plus or minus? Oh, it's multiplied. I wasn't sure. So it's just multiplied. Okay, cool. And sigma of y squared minus sigma of y squared. And obviously, if you get a little lost here, like it's okay, right? It's really okay, but this is going to help us, okay? This is going to help you understand what it is. Like we know what is it doing. We're just trying to make this line a best fit. That's all our goal is. Our whole goal is just to get this line. And how can we get this line, or how can we get this value? Like the line of best fit's kind of tough, and the R is just showing you how strong that line is. But basically, when you put it in the computer, it just spits out the R. But I want to show you where it comes from. How can they tell you how strongly correlated two variables are? So this is your R value, or your correlational coefficient. Can be positive, it can be negative. It's going to be between -1 and 1. The n here is just the total number of terms. This is your predictor variable. Your y is your outcome variable. Now, what does sigma mean? It means add them up. So basically, we have to take all of our terms, we multiply by every one of these terms multiplied together, and then we're adding them up, minus all of the x terms added up times all of the y terms added up. That's all that means. Then we've got this one, which is n sigma of x squared minus sigma of x squared. These look almost identical, right? But this one means we're squaring all the terms first, then we're adding them. And then this one means that we're adding them all first and then squaring them. The parentheses just gives you the order. So we square, we square, add, we add, square. Same thing here. So we square, add, we add, square. So we can make stuff up. We can give ourselves some data, or we can use one of the data that are there, but I'll just make up something small. But it's really not too crazy, I promise you. I'll use Excel to do it, but it's really not crazy at all. Just so I don't have to like repeat multiply a bunch of times. So let's say, I don't know, we'll do study time in hours. And then we'll have grades on a test, on test 1. So let's say you studied 1.5 hours and you got a 78. Let's say you studied 2 hours and you got an 80. Let's say you studied 3 hours. Let's say you studied 1 hour and you got a 65. Let's say you studied 2 hours again and you got an 82. Let's say you studied 2.5 hours, you got a 91. Let's say you studied 3 hours, you got a 96. Let's say you studied 2.75 hours and you got a 97. Let's say you studied, we'll make it 2.5. I don't want any of the numbers to be too crazy enough. And let's say you studied 4 hours. Oops. So you studied 4 hours and you got a 99. Okay. That's probably not enough cases to show that it's significant, but at least we have some value. So I have 1, 2, 3, 4, 5, 6, 7, 8. Might as well make 10 students. You studied 3 hours, you got an 85. You studied 1 hour and you got a 62. Cool. Now I got 10 students, so my N is 10. So it's easy numbers to work with. So I'm gonna use Excel with this data, and I'll kind of show you exactly how to make this crazy thing happen. And then I'll show you we can just click the button, it gives you the R. So let's open a random book. And we're gonna make this happen. Get out of my way. Okay, here we go. So we're right here. Here's the data. Let's put it in first. Sorry about my messy handwriting. I know I'm not the neatest. I got a comment that I will work on, I promise. So we got study time. And we got our grades. And we can't like order these. If we do order them, which is fine, you have to make sure you sort it. Perfect. 11 because we used the top line. All right, next one. Our test grades, 78, 80, 65, 82, 91, 96, 97, 99. What else we got? 85 and a 62. Cool. So these are our terms. We can think about this as our X value and this is our Y value. Now we got to do some moves. So basically, I'm going to just I need to sum these. I got to use a bunch of these ideas. So let me just move myself out of the way. All right, so the first thing I'm going to do, I'm going to actually take this one and move it over. Actually, here, let's just order these first, just so our data looks nicer. And we're going to order these first. So sorry, let's just leave it here for now. If I take this and I want to sort this, just remember I have to expand it because they all have to match. Cool. And it should look like it goes up pretty much the whole way for the most part. Okay, so the first thing I want to do is I want to have a squared term. So I'm actually going to take this column and put it here. And I want to make this term my X squared term, because we know we're going to need these squared. So that's the first move I'm going to do. And this is going to be my Y squared, because I'm going to have to square all these. And then I'm going to need an XY term. And then I'm pretty sure I need an XY squared term. I'm not sure. I could look right back. I'll start here. So basically, what am I going to do? How am I square this? I'm going to do 1 times, I'm just going to do times itself. That's squaring it. Cool. Now, if I drag this down, they're all going to get squared. Magic. Perfect. And we have to sum all these. So I'm going to have a little sum at the bottom for each term. So I'm going to get a little sum, auto sum, boom. You can do equal sum as well if you want. That's what the sigmas are. Those are all those equal sums. And we want B2 to B11. Perfect. And then we can sum it by doing equal sum. Here's a third way to make your sums. A third way to make your sums. Oh, sorry. If I do sum and I can drag. That's the third way you can do it. All right, now we need a Y squared, which is going to be simple, equals this one times itself. I can drag these down. And then it automatically does them. That's why I'm using Excel, so I don't have to like multiply a million times. And I'm going to sum this, so equals sum. All right, cool. So I think I need an XY. Do I need an XY? I do. It's the first thing we need. So here we go. So I need the sum of all of the XY terms put together. So how can I make an XY? Well, it shouldn't be too hard. It's the X times the Y's. So remember, study time is, I should just put an X next to it. So we know this is our X. And I'll put a little y next to here because we know that's our y. Oops. Want to also notice this grades, just so nobody's confused. I have the first one. I can drag all these down. Ta-da. Then all I have to do is sum this one. And sweet. All right, so I have all of these terms. Let's see if I need anything else. And xy minus all of the x's times all of the y's. Okay, yeah, I think we should be pretty good. I think I have everything. So I'll just do the top part and then I'll do the bottom. I think I've got everything I need. Yeah, I should. So like most math, it gets confusing if I don't do like a little piece at a time. So let me move my floating head over here. And here we go. Let's start. So the first one is n. We're just going to do the top. Or in our case, is the numerator. So our n is how many terms? 10. And the first thing we have to have multiplied by this is all of the x times y. So all of your x times y is 1977. It's a good year. Lots of good comics came out that year. And I have to minus all the sums of the x's times all the sums of the y's. Well, we have our sums of all the x's right here, not squared, so that's 22.5. And all the sums of the y's are right here, which is, oh no, all the sums of the y's are right here, which is 835. As I said, I'm just doing the numerator, so that's what I'm going to do. I'm going to have Excel help me though, so I don't have to like think too hard. I can even write numerator here if we want. So it's going to be equals 10 parentheses 1977, or we can click the box, right? 10 parentheses, this box. Then we're going to do minus parentheses, and we just need what? The sigma of x times the sigma of y. And here's the sigma of x times the sigma of y, which is 835. And if you want to do this a different way, you could obviously put a parenthesis here. Oops, a parenthesis here. Sorry, it doesn't want to be my friend. I have to click there. And I put a multiply here. I think that looks nicer. Because then they're both in parentheses and it just looks nice. So what is our numerator? 900. There's our top, 982.5. All right, now we need our denominator. The denominator has a bunch of parts, but that's okay. We can do it any way we like, but I can write them here first if we want to. So the denominator is the square root. I'll wait on square rooting it first. I'll just do it. So it's 10. All of our x squareds together, right? We did all of our x squareds first, and then we added them, which is right here. So 58.75. So it's bracket 10, 58.75 minus, and now we need the sigma of all the x's squared. Well, all of our x's squared are 22.5 squared, which basically means it's times itself, but yeah. So that's the first bracket. Then I have to minus the same idea. So then it's going to be minus same idea. So it's 10 parentheses, all of the y's that were squared first, and then added together, which is 71209. And we have to subtract what from that? All of the y's added together normally, which is 835. Then what do we do with that? We square it. So that seems like a whole mess. Seems like a whole lot, but it's not too crazy, right? It's not too crazy. So that's what I'm going to do for the denominator. But then I have to square root it. But before I square root, I'm just going to write the denominator, which we know is going to be equal to 10. I need a parenthesis because it's a bracket. So it's 10 times okay, so the 5875 B2 minus, I'm gonna put another one here because I'm gonna do this one times itself instead of squaring it, so I don't have to write extra stuff. 22.5 times is 22.5. That's the first half. So close. I guess I need a third close, do I? 1, 2, 3, 1. Yes, I need a third one. So this closes that bracket. They're all together now, which is nice. Now I subtract, double bracket. I need 10 times. The first thing is the 71209, which in our case is D12. Minus, I'm gonna put another parentheses here, and now I need the 835 times 835 times. I have an extra set of parentheses here, but I just like to be clear about everything I do. So close. So that's the whole denominator. I know, exciting stuff. 10, we've got the sigma of x squared minus sigma of x times sigma of x, 10, which is Rn times y squared, the sigma of y squared times the sigma of y times the sigma of y. Cool. So we've got a negative number, which is probably not great. So I could have messed up somewhere. You know what? We're all human. So these numbers are way bigger than these numbers. But when it got squared, it should help. No? Okay, let's see what happens. So I have to take this now and take the square root of it. But when I square root this, it's going to be an imaginary number. So see what happens. Yeah. So it's an imaginary number. So there is a mistake somewhere. What is the mistake? I'm not sure. Oh, haha, I see the mistake. So remember before where I said, what's between this? Is it add or subtract? But it's multiply. For some reason, my brain still thought it was add or subtract. There should not be anything here. It should be multiplied. That's why it's weird that I got a negative number. So obviously math, you know, you make mistakes. You can't square root a negative number. I think you can, but I'm not the biggest on convention. Here's our value. Let's get rid of this friend. Okay, so instead of just having the parentheses here, I have to just put a little multiply sign. There it is. There's our denominator without being squared. Sorry, made a little mistake by putting a minus sign there. I apologize. So we have to take the square root of the denominator. So the denominator square rooted. So equals square root of the value above it. Ta-da. So it's this divided by this is going to be our R. So here's our R. We want to do a baby R. And we have our numerator divided by our square root of our denominator. And here it is. It is a very strong positive correlation, which is what I made. Oh, sorry, that's just the R. So it's positive and it's big. Let's do our R squared. So how do we do R squared? Well, we got R. So to get R squared, all I have to do is multiply times itself. It's going to be a little less strong than I thought. 0.799, still very strong. So we got our R squared. Now, that was a ton of work, but we got our R value. Now, what is the good thing about programs and stuff like this? That this is going to show you exactly if I do just these two together, these numbers and these numbers. So here, I'm just going to put them over here. And I take the Y. I like it next to each other. It's just easier for me to work with them. Okay. Now, if I insert a scatter plot, boom. Oh, and I don't know why I have such an outlier. Oh, here's why, because I have the bottom. So you never want to include the bottom. So look what I can do. Get out of here. Sweet. Here's our scatter plot. Isn't that nice? So we can. Well, we don't need a legend. Our axes look pretty good. The x-axis was our study time. I'm just going to call it study time. And then I'm gonna do our grades. Whoa, sorry. I have so many things open. I'm just building another course. There's our study time, and I'm just gonna put on our grades. You could change this, right? We can shift this if we want to see it more clearly, but because it's a grade, um, I hate that there's 120 up here, so I gotta get rid of that 120 for my vertical axis. So I'm going to actually get rid of 120. I want it right at 100. I don't care that somebody scored like 99. It doesn't matter to me. I like that. And if I want to, we can start at 50. We just have to let people know that we started this graph at 50. A lot of times we do this for when we start graphs lower. Just it's like kind of looks like a heartbeat. And this allows us to jump from 0 to 50, or like actually just start at 50, right? So we can have our points do what we want and not have them all there. It's called something I just totally forgot. Oops. To jump from 0 to 50. Okay, and I just want to call this grade test grades. And what is our actual chart name? It's not grades in Y, it is study time versus test grades. You can make it whatever you like. I like having a good title. Here we go. Awesome. Okay, so what is one more thing I'm going to add? I'm going to add what's called a trend line. What's the trend line going to give me? It's going to give me this exact thing that I want. And it's also, if I put on the equations and values and the R squared, it's going to give me the values. So this should tell me everything we need to know. Boom. So look at our R squared. What does it say? 0.7992. What did we get? 0.7992. The magic of mathematics. We have our correlation right here. Looks beautiful. We have our R, we have our R squared. We've got everything we need. This is the equation of that line. This is telling me the y-intercept and the b, you know how that formula had the b in there? Well, there it is. There's our b value right there. Now, I'm going to use this data on StatCrunch, and I will show you it does the same exact thing, but I'm sorry if that was too fast, but this is all kind of by hand, and this is just the computer pooping it out. 0.7992, all that work to 0.7992. All right, so let's go to our StatCrunch and check it out. Okay, wild. Oh, because I'm doing a Zoom video with this. Okay, so let's go to my Math Lab and Mastering. And I'm going to I'm going to open this. And then we'll go through the book and whatever it needs, but I thought it'd be really important to show you exactly how it spits out these answers. So let's go to StatCrunch. Let's just go to the website. And let's see how you find the correlation coefficient and draw the scatter plot. So we'll learn it together as soon as it wants to open. I'm just clicking different things, see if something will open for me. Nice. I'm just going to take a data set, whatever one it is, then just put in these values. New data table. Here we go. All right, well, the website's not being my friend. Isn't that annoying? All right, let's see if we can make one. Anyway, with just this data. Okay, we'll see if the systolic and diastolic blood pressures are, the same. So let's go to a scatter plots. We'll make our X value systolic. We're going to make our Y value diastolic. Group by, that's fine. No, that's okay. That's okay. We want the points that let us put a line through it. Okay, let's see if we can have both. I'll see if I can add a line. Let's look at it. Oh, that was a terrible, terrible decision. The lines were not what we wanted. Let's try that again. Plots. Systolic versus diastolic. I'm assuming this will give us some sort of positive one. Sweet. This one looks like it's slightly positive, right? Slightly positive. Okay, let's see if we can get the regression line on top of it. I'm sure we can look, I'll look it up and see exactly how to do it for the next one. All right, let's see if I can calculate a regression. We want a simple linear regression. Our X1 is going to be, we're going to see if the systolic has any effect on the diastolic. This hypothesis testing just means that there's no difference. And we basically, if we want this A, it's not equal, but if we want to say one is bigger than the other, like one-tailed versus two-tailed, which I'll go over. We've got a graph. All right, let's see this. We got our degrees of freedom, our F value, our P value, and we have our R squared, which is usually what we're looking for, and our correlational coefficient right there. So it's going to spit this out for you this way. Kind of don't like that they didn't put it on the graph. I'll have to figure out a way to do that. I'm going to try to use my data one more time. Nice. Haha. Look at this. I will not be denied. Oh, so I have to do this. Sorry. Study time. Grades. Cool. Elite row. All right. Labels. All right. Well, might as well just build this thing. Compute. Sweet. Here is ours. Looks just like mine. And let's do the regression. Stat regression. This is simple linear. I'll explain all the differences if you want, but it's just one predictor, one outcome. That's all that means. We want to know if study time can predict the grades. Indicate that. Residuals is nice. Histogram residuals. Fitted line plot. These are just things you can add on to it, which is really nice. I'm just gonna add some stuff and see what happens. So that's really what math is anyway. Do some stuff, see what happens if it works out. Cool. All right. Is that the same one? Yep, there's our 0.799, and here's this one, and there's our sample size. We've got everything, which is cool. Oh, cool. And you get it on the next line. So you just have to click to the right, and there should be our line right through it. There's our fitted line. That's the one we wanted, the red line, the progression. So we've kind of got everything. I didn't know you could click to the right. I forgot. So beautiful, beautiful, beautiful. Okay. I think it's time to look at the book. So you do it on StatCrunch. You get a bunch of extra information, which is really nice. Can you do it on Excel? Yeah. Of course, you can do it on whatever program fits your fancy. I'm always going to show you both. If you want to do a regression on Excel, like do a regression on Excel. I remember I've seen it before, like the exact formula. I'm just gonna click the YouTube one because I don't remember what to click. I know you have to like upload data. You have to activate it. Yeah. Whoa, he's loud. Way louder than me. I know you have to click something to activate the data. There it is. It's the add-ins. Cool. So if you want to do it, you have to go over here on the right. Here, the data is not available. You need to activate that option. Go to File, Options, Add-ins. All right. Let's make it happen so I can go to regression. Obviously, we saw it on the graph, but I'm always going to try to give you more information. And I've done this before. It's just been some time. So you said File, Options, Options, File Options. Options. Okay, English. I like that. That's all it's letting me change on this one. Oh, you might have to get the downloaded version. That would not be nice. Let's go to analyze data. Ask a question about your data. That's cool. So we need data and we need an analyze data button, but it's just giving me this weird chart thing instead of giving me the options because I haven't like uploaded this one. Queries group. Okay. How do we put that in on the web version? I know I have it set up for my desktop version. Here it is, the tool pack. All right. So for Windows, click the File tab, click Options, and click Add-ins. Right, we'll do this one at a time. So here we go. Click the file. Ooh, click the file. Click the options. And then click the add-ins category. It doesn't have it. So you actually have to download the regular Excel to do it. I'm sorry. My bad. It didn't exist. We saw it there. So go to options. And then we go to, just so you can see how to do it. I'll look at it again real fast. So we go to File, Options, Excel add-ins, go. File, Options, add-ins. And okay, so we're at add-ins. I guess I just have to go to Go. And in the add-ins box, click the analysis tool pack. There's the analysis tool pack. I'm going to take them both. Why? Because honestly, actually, I'll just do the regular one. I don't know what VBA is. And we click go. Oh, here it is. Nice. Click OK. And you should have it. Now we should be able to do this. Just so you can see all the other pieces. So here was our data. And now, sorry you can't do it on the web version. That kind of sucks. We can go to data. Data analysis. Sorry, that was a pain. Go to data analysis, and we want a what? We want a regression. See, notice it's got a ANOVA now, which we're going to do. I got a regression, it got a correlation, it's got kind of everything. So let's do a regression. We know our input range. We click on this. And here's our input. Oh, and we can have labels. That's cool. So we got labels. Here's our, oh, it's Y first. That's annoying. Sorry. So they want the Y first. Am I complaining? Nope. Then we're going to do the X's. Here's all the X's. Labels, confidence interval should be 95%. Do you really need it? Not so much. We're going to have the line of best fit plot. We'll have some residual plots. You can click what you like. I'll show you what you really need. Let's click OK. See what it spits out. Ooh. That's nice. That is quite nice. Quite nice. What do we care? We just want the R. Boom. It's right there. It is right there. There's our regular R. There's our R squared. So pretty. Doesn't give us the graph. I guess you got to do the graph by hand, but that's so nice right there. Awesome. And this is super significant. I made it set to be very, as long as it's less than 0.05, you're 95% sure. Okay. Wow. That was a lot. That was a whole bunch of a lot. So let's look at the book now that we've done it on StatCrunch on Excel graphically, and then on Excel the other way. So you can't do it on the web version. You actually have to download the regular version onto your desktop in order to get this data thing. And then you just go to data analysis. You got all this extra bits. Okay. So what's the difference between correlations and regressions? Oh, man. Honestly, not much, but we'll get into it. So I hope you're ready. We're finally ready for the book. I'll do some of these questions, 1, 3, 5, 8, 9, and 12, but we're going to 2.4. I hope you're as excited as I am. So, e-text. And I'm going to chapter 2.4. Here we go. So, correlation exists between two variables while one variable is associated with the other variable. A linear correlation is that line, or the straight line that we're looking for, and the scatter plot are all the ordered pairs, your x's and y's of data. Exciting stuff. Correlation does not say it caused it because we didn't manipulate it, so we cannot prove it without the confounding variables. This looks like a positive correlation. Very pretty. This looks like a no correlation. Looks pretty flat. These look very grouped up, which is weird, but I would go with this as a negative correlation. But there's a gap here. Okay. Linear correlation coefficient, or R, which is what we're finding, is the measure of the strength of the association between the variables from -1 to 1, which is nice. All right. Correlational coefficient, how you find it. They're just telling you to put it into the book. You could put it into StatCrunch and just let it spit it out, or you can make the picture. I'd recommend making the picture and then just turning on the graph, but then you don't get this value. So It's a hard choice to make. All right, okay, so this is the critical values, which is very important. It's very important. So what does the critical value mean for this stuff? So the critical value is probably the most important thing we're going to see for this. Basically, where it comes to tails. So I'm going to explain this business. And remember, this is where this stuff gets challenging. So I'm here. Bother me. Ask me questions about it. Okay. So, all right. So let's say we've got this thing. It's like a picture. This is like if we're thinking it's one-tailed. This is if we're thinking it's one-tailed the other way. And this is if we're thinking it's two-tailed. Okay. So what do the critical values mean? I'm going to try my best to explain it. I don't know why it looked really weird. So I'm just going to reload the page real fast. So what does it mean by critical values? Okay. And they give you a bunch of them. Number of pairs of data, critical value, cool. So if we have an N, if we have 4 cases, just 4 cases, we need it to be over 9.5. If we have 5 cases, it's got to be over 8.78. If it's 6 cases, so the bigger your N is, the more peeps you got, right? The more people you got, that means the lower you need to be significant. Isn't that cool? So notice that it's positive and negative on this one. This is if it's two-tailed. So what is this really strange picture trying to show you? So let's say we had, I don't know, get out of here picture. Let's say we had 7 people in our study, right? Or 7 cases. So this is 0.754. If we're anything bigger than that, right? If we're anything bigger than that for R, we know it's significant. And let's say we are at a negative 0.754. Anything less than that is also significant, okay? If you're in the middle, it just means it's no correlation. You can't say that one predicts the other. Can't cause the other, just predicts it. Now, if one tail, these are like one tail businesses. So one tails, that means we're only going to say it's positive, or we're only going to say it's negative. That happens a lot for t-tests and things like that. But if we really are saying that the test grades are going to be a positive, we're only going to look at one side. You can't like kind of switch it at the ends. All right. So alpha and p values, what is that? So the p value, that's a probability of it not occurring by chance. So the lower the p value, the better you want, right? So if this is 0.754, our p value just has to be 1 minus 0.754. If you get confused on how to do anything like that, guess what? Let your calculator be your friend. 1 minus 0.754. This means 0.246. This means we have a 24.6% chance that it's due to chance. And this is like, we're 75% sure it's not due to chance, it's because of the study time. And here we're like, it's 24% due to chance. That's what the p-value means. That's where it comes from. We usually use the what? The 0.05. 0.05 is for like all social experiments, like psychology and stuff. So this is like for social sciences. But if you want to test a drug for something, you really can't with a correlation for sure. It can be done, but it's usually not. We got to be for medicine. We got to be 99% sure this thing is not. Sorry about my spelling. It's not due to chance. We got to be 99% positive about this stuff. All right. Height and shoe length. All right. So what is the regression? So given the paired of data, the regression line or best fit line or least squares line is the straight line that best fits the data. The specific criteria, the line of best fits described in 10.2. So they give you this business. The regression equation this is y. So this is your predicted. Sorry, this is your outcome. B0, this is your y-intercept. This BI is your slope, and this is your X. This is your predictor variable. It should look familiar to you. It should look like y equals mx plus b. I don't know if you've ever seen that before, but any line, no matter what line it is, that's your slope. Didn't disappear. That's your slope, and that's your intercept. And it works the same way. It works the same way for this. B0 is your intercept, and that's the slope of that. Now, to get this, oh yeah, they say it. You can use it by the software or something like that, but normally it should give you the parts. So let's see if we got our parts in our hours, right? Let's see if they give us an intercept. Let's actually look at this line. We'll look at the results on both, right? I'm always going to try to show you on both. So let's see if it gives you a B value. Regression, this is your degrees of freedom. This is your sum of squares. This is your mean squares. There's your F value. That's your significant level. I don't see a B here. Now, you know where I do see the B? When we did it the first time, or we do it right here. A really easy way to find it is just inserting the scatter plot and just putting the line in and putting the equation on the line. Boom, boom. So here's your B, 56.92. That's your B0, that's your intercept, and there's your slope, 12.092. Let's see where it comes up on our stack crunch. All right. Look, it's right there. There's our slope, 12.092, 12.092. And what's your intercept? Right here, 56.292, 56.292. I'm just seeing where it is on the summary output. Oh, here it is. Man, I am so blind. I am sorry, everybody. Here it is. There's the 56.292, and there's a 12 point. We have it. We've got our intercept, and we've got our slope. So doesn't matter if you use the graph of the scatter plot, the data points of Excel, or StatCrunch, you've got every piece you need. Very cool. All right, let's keep it going. Okay, so the most important thing, oh, it's the end. So cool, I get to explain some shit. I'm sorry. I get to explain some stuff. So I think this is the most important part. I'm going to use my data from the beginning, right? Study time, grades. What does this mean? Let's actually do something with it, right? So we have this mess of data, right? We've got this mess of data. We know it's significant. Isn't that cool, right? We know it's significant. Doesn't matter which one we use. We can look at any one we want. So this is our equation, in case you don't know. Our equation looks like this. Y equals, I always like, they like putting the y-intercept first, so I'll do that. 56.29 plus 12.09x. So what does that mean? This means, okay, this means for every hour you study, it is predicted that your grade will go up 12.09 points. Isn't that wild? And then you put the equation, right? We have everything here. So we have our F significance. I'll actually write the real equation. I just forget this sometimes, but after you say the sentence, we just have to put it in, which isn't too crazy. All right, this little piece is going to be really helpful for us. Sorry, my phone keeps yelling at me. Um, all right, so I really like using the statology one, the one that I showed you. So that's what we're going to use. Um, a simple linear regression was used to test if I'll type it. A simple linear regression was used to test if study time in hours significantly predicted test grades. The fitted regression model was, we can literally just write the equation, y equals 56.29. This is how it looks like in the research papers. 56.29. 29 plus 12.09x. Nice. 12.09x. All right. And then it's our other one. Weird ads. All right. Sorry. I don't know how to get rid of it. So the overall regression was statistically significant. Can you put parentheses? R. I'm just going to do raised to the 2 equals. So we know our R squared value. We got that 0.799, comma, F. So this is the F statistic. This is where they were getting. So we have to put our degrees of freedom. So our degrees of freedom is what? Our degrees of freedom is always going to be 1 less than what we have. So what is 10 minus 1? 9. It's usually n minus 1 for these. So it's 9. And then we have to put what it is. So it's equal. And this is if we also want to put the residual. So degrees of regression, degrees of residual. So we can do 1 comma 8 if we want. I usually just like putting 9, but if you want to be fancy, you can put 1 comma 8. And then we do equals the F value. Our F value was, our critical value for this case is 31.85. And then all we have to do is comma P. Because our P is so small, we're not going to put 0.0004. We're just going to put it's less than 0.001. Whenever it's, oops, sorry, whenever it's that small, you just put it's less than that. Ta-da! And there it is. This is how my little study would look if we actually wrote it up. All right. Hopefully that was useful. I never quite know what the best thing is for this, but I just thought showing by hand, going through all the programs would be great. So we get to do the problems. I hope you're as excited as I am. All right. So 1 through 3, 5, and 8. I'll let you do the last one yourself. So 1 through 3, 5, and 8. 1 through 3, 5, and 8. And maybe I'll do the other ones because I know this stuff is tough. All right, so here we go. 2.4. Okay. In this section, we use R to denote the value of a linear correlation coefficient. Why do we refer to the correlation coefficient as being linear? Um, I think probably the best thing to think about for number one is that we are creating a straight line, right? That this is like a straight line that we are actually building, and we want to figure out the line of best fit for that. So let's see what the book says about it. I always want to make sure that I'm not giving you misinformation, but I think it's because we want the line of best fit. It can be because we're approximating that line. So it's the best way to look at this between it, and it's going to be that straight line. I think that's what they mean. We're trying to find the best line to draw through all these to make the best prediction about how this works. And why is this useful, right? Like, I think that's the most important thing. Like, why is it useful? Because, like, in our case right here, you can be like, man, if I normally would have gotten like a 70 on this test, but if I studied like 3 extra hours, right? If I would have had like 36 more points, I'd have like 106, right? So you can predict your scores. You can predict how something might happen, and that's where the line is really useful. So I think it's because it gives us a better sense of a prediction by using mathematics. That's what I think the real answer is. So to me, I think it's a better prediction using a linear model because we can determine outcomes based on inputs. That's what I think. Or you can be like the straight line best approximates the distance between all of the points. However you want to say it. Okay. Hopefully that was some good info. All right, let's try number 2. Whoa. Number 2 says, a study has shown that there's a correlation between body weight and blood pressure. That's nice. Higher body weights are associated with higher blood pressures. Can we conclude that gaining weight is a cause? No, we cannot. This is a number 2 is a big no. Okay. Why is number 2 a no? Sorry. Why is number 2? Number 2's gotta be a no. Because correlations are predictors and other variables can be at play that created the change. So we can't say it caused it. Correlation does not imply causation. All right, number 3. Theta to numero trace. What is a scatter plot and how does it help us? So scatter plot, if I click, sorry. Scatter plot is all of the ordered pairs. So basically your XY for a predictor and outcome variable on a graph. This shows the general trend of the data, and we can infer positive, negative, or no correlation. Nice. All right. That was 1 through 3. Let's look at 5 and 8. 5. In 5 through 8, use the sample data to discuss your scatterplot. Use the variable first for the x. Would you conclude about it? Oh, cool. So they give us one. We might as well do it. I feel like I use them both, but I'll use this guy just for the fun of it. I just like Excel better. I didn't think I would. I thought StatCrunch would be the one to use, but I don't know. I guess I just like the Excel better. So we've got number 5, height, actual height, and predicted height. So does our height actually predicted height? Oh, so it's weather. So the actual high and the predicted high. Use the first variable for the x-axis. So we're using the actual and see if that makes the prediction. I would go the other way around because says predicted on it. But guess what? That's not my example. To me, this would be X and this would be Y because it has the word predicted in it. So I'm fine with that. I'm not going to argue with the values. So 80, 77, 81, 85, 73, 73, 80, 72, 83, 81. All right, let's do the other ones. 56, 57, 59, 56, 64, 57, 61, 63, 59, and 61. So I have everything. So I'm going to click this, go to home, sort this. We have to expand it because these are all linked. And all I'm going to do is make a picture. I'm going to add in the trend line. And it's off. It is so off. And I'm going to also put the equations, boom, boom. So it's basically no correlation. 0.2, to me, that's no. It's moderately negative. It's very low, right? That's barely sloping downward. I'm going to go with negative, but let's also use it. Let's go to data. I hate title. Oh, man. It just kills me when it doesn't say the right things on it. But that's okay. So inserts, data. We need analysis. Let's do a little regression. If it will let me. Data, analysis, regression. Okay. So we have the Y range. Is this what they want for Y? The X range. Wow, it's already automatic. That is so nice. Let's click OK. Oh, I hit an extra thing for this one. For X range. Boom. All right. Sorry, it keeps being weird for me. Here we go. Our R squared still is that 0.22. We know that the intercept is 82 degrees, and then it's going to be down negative 0.3 the whole time. So that's the information. So yeah, that sounds good. Sorry, this was predictor. Nice. Okay, so that was the information for 5. It's slightly negative or no correlation. Let's see what else we got. Some of these tabs out. All right. That was 5. What's the next one? I believe it's 8. Table lists the pulse rates per minute. What is a major fundamental flaw with this exercise? The table lists pulse rates, beats per minute from randomly selected females and randomly selected males based on data 1. What is a major flaw with this exercise? They should be linked, I think. Let's discuss this. Use the first variable as the x base. What do you conclude about it? Well, the first one we can conclude that this is not a great predictor. The second one, what is a major fundamental flaw with this exercise? Each of them should be linked, like this should be a males on 2 things or females or both. These are 2 separate pieces of data. They should all be together, right? It should be males, this and this, or it should be males and females on the same pulse rate. Like it's off. They're not linked in any specific way. It wouldn't matter if this male 60 is here or here. The major problem with this is that they're not linked at all. So that's the big issue here. I'll do this one in StatCrunch, but basically, the major flaw with this exercise is that they're not linked in a fundamental way. And that's what a correlation means. We want to say the prediction of female occurs in males. Like the female score should predict the male score, but it doesn't really make sense. So that's the issue. So let's do this one in the StatCrunch. All right, cool. Let's call this male. Wait, how do they want me to do this? So we got male and we got female. So they want females X, so females first. So we're gonna call this female. I'll call this male. Get rid of the residuals. I'm pretty sure I can just click this whole column. Perfect. All right. So female 66, 56, 82, 78, 86, 88, 56, 36, 84, 76. All right, let's get the males. 60, 52. For some reason, the males were more calm. Interesting. 62, 52, 76, 52, 62, 72, 64, and 78. All right, so let's do it. So we're going to do, ready, a regression. Where you at? There's my regression, simple linear regression, my X variable, they want female, my Y variable, they want male. Fitted line plot, that's all I'm going to put on it. Let's go compute. It says it's significant, 0.002. This one isn't though. Yeah, 0.835. Nope, it is not significant. Nice. So the F stat is this, the P value is this. So this is not a significant one. I didn't think it would be anyway, but let's look at the data. Yeah, it's almost completely flat. Beautiful. And what's our R value? Our R is negative 0.07. R squared is 0.0. It's almost negligible. Cool. All right, so let's go to, I might as well just see what the other ones that they have you do are. 9 through 12. Linear correlation coefficients in exercise 9 through 12. Use table 211 to find the critical values based on R. Based on a comparison of the literal coefficient R and the critical values, what do you conclude about a linear correlation? Using the data from exercise 5, forecast and temperatures, the linear correlation coefficient is negative 0.574. All right, so let's look at some of these critical values. So 9 through 12. This was in exercise 5. No, that's example 5. I believe exercise 5 is just the one above it. The forecast. Okay. Table is here. Okay. All right. So if you're giving this to us, so I got to go back to where my temperature one was and look at it. I believe I did this one on Excel, right? Using forecast, the linear correlation coefficient is negative 0.475. What did we get? We got 0.22. Oh no, just mere multiplier 0.474. They got 0.475. Yeah, it's the same thing. 0.474, 0.475. Okay. So we got 0.475. It matches. That's cool. So the linear correlation consists. So find the linear coefficient R. Oh, it's provided. Use table 211 to find the critical value. Okay. So we have to go to table 211 to find this critical value and see if this is significant based on that. Whew, how crazy is that? Okay, so we have ours, which is 0.475. It's negative. Was our picture negative? I believe it was. I believe our picture was definitely negative. Yes, it is. Cool. 0.475. I like it. All right, so let's check it out. Now let's go to this table. Let's see if it matches. I gotta go to Pearson. I gotta go to their tables. Maybe it's in the chapter. So table 2-11. Well, if it looks like this, I might as well just look up table 2-11. Might as well. Let's find 2-11 table. That's 2-14, but that's a figure. Here's 2-11. Sweet. So we know we have 10. We have 10 pieces of data here. We got 10 pieces of data right here. 2, 4, 6, 8. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it's just double, but each piece of data actually has 2 components, an X and a Y. That's why that male and female did not work. If we're on 10, our critical value needs to be 0.632. So we have to be what? Greater than 0.632 or more negative than negative 0.632. We have a negative 0.475. It is not bigger. It is not more negative than this value. So guess what? We can say it is not significant. I know we saw it on the graph, but using the table, like if we didn't have Excel and we just looked at the table, when I did stats many a moon ago, we had to use the table. So 9, negative 4, negative 0.475 is not less than the critical value. And our critical value is 0.632. 0.6. Sorry. Which means this is not statistically significant. Basically, we have to say that there is no, it's not, cannot significantly predict the weather, right? That the actual does not predict the weather. All right, I'll do 10 also, just to make sure this is clear for everybody. So number 10. Number 10 says, using the data from exercise 6, airport data speeds, it says it's 0.866. We have an R of 0.866. We can do it again, but because we have a table here, well, how much data is in 10? Is in exercise 6. How much data do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. We only got 9. So 9 is 0.666. That's a critical value. And ours says 0.866. 0.866 is bigger than 0.66. So this is statistically significant. That's what that means. The R value is greater than the positive R value is greater than the critical value. And thus, the study was statistically significant. What does that mean? What does that actually mean for us? Well, we'll go to number 6. We'll see what that actually means. Number 6 says, cellular data speeds from Sprint and Verizon measured at 9 different airports. What is the correlation? So we can say the cellular data speeds for Sprint can significantly predict the cellular data speeds of Verizon. Now, what would I do here? I'd actually put the formula. I'd have the F with the degrees of freedom. It would be 1,8 for the 1,7 for the residuals, because 8 is 1 less than our full degrees of freedom is 8, so those have to add to 8. Then I would put whatever this value is. And then I would put the rest of it, just like we did over here. For every hour or you stay, the grade will go up 12.09 points, and I would just have a simple regression was used to test the study time, was used to test Sprint's cellular data speeds, to test if Sprint cellular data speeds significantly predicted Verizon cellular data speeds. The fitter regression model was whatever we got for that, and the overall regression was statistically significant, but this would be a 7. I don't know the rest of these numbers because we didn't do it, but that's how it would work. This is a super long video. If you made it to the end, congrats. I did just about everything. There will be more. There will be more information about all of this, and I will explain it. And enjoy your day. Take care.